Hello everyone, I'm Rana, one of the author of this paper. Today I'm going to present the paper called An S-box Design Using Irreducible Polynomial with Affine Transformation for Lightweight Cipher. I want to acknowledge our other authors, Quazi, Mamun, and Rafiqul. Cryptography has a crucial impact on the data security of IoT communications. Block cipher is one of the most popular symmetric algorithms used to encrypt the plaintext to ensure secure data transfer by providing confusion and diffusion properties. S-box provides Shannon confusion properties to hide the relationship between plaintext, ciphertext, and key. Therefore, designing a robust S-box is essential for a reliable and robust cipher. A block cipher like AES S-box consumes more time and memories, which is not suitable for the IoT devices. Subsequently, an S-box needs to design for low-resource IoT devices. S-box and security. An S-box can be split into two categories such as dynamic and static. In case of dynamic, the S-box changes regularly in each session, make the cipher harder to break. However, the same S-box uses in every session in the static status, which is less secure but requires less memory and computational power. The Latin square dynamic S-box method provides the increased security level of the block cipher and requires more memory that IoT devices cannot afford. On the contrary, it is very hard to identify the relationship between plaintext, key, and ciphertext in case of dynamic. However, in the static, is not that hard and data communication is less secure. Security of IoT communications. Therefore, it is challenging to trade off between security, memory consumption, and complexity of S-box to secure communication between the resource-constrained IoT devices. AES hardware requirement is significantly high, which resource-constrained device may not afford. An 8-bit S-box requires a relatively higher hardware area and memory than 4-bit S-box. Therefore, the 4-bit S-box has typically used a much more cost-effective hardware area than a 8-bit S-box such as Present, LED, and Simon etc. Several approaches have been initiated to generate an S-box, such as analytical approach, chaos-based approach, cellular automata, dynamic key dependent, etc. However, the most methods are energy consuming and may not be suitable for low resource IoT devices. Therefore, in this paper, we proposed a design of S-box which will be suitable for resource-constrained IoT devices. We suggested an S-box creation process based on 4x4 bits, which is suitable for lightweight cipher. We use the irreducible polynomial equation and affine matrix in this construction method. Empirical results show the suggested S-box offer robust defense to differential and boomerang cryptanalysis. Proposed S-box generation. There are three steps involved in this S-box generation. First step: selecting an irreducible polynomial equation from Galois-Pill 2 to the power 4 and create the hexadecimal table from those polynomials. Step 2. Generate multiplicative inverse table from hexadecimal table. And step 3. Create S-box transforming the affine matrix. To generate the hexadecimal table, we followed the following step. Create a list of polynomial for GF2 to the power 4. Select irreducible polynomial equation from the list and then create hexadecimal tables from the selected irreducible polynomials. Irreducible polynomials make the nonlinear permutation function that has diffusion properties. This system distributes input bits in a nonlinear way to output bits, which creates confusion. According to the table, we found three irreducible polynomials from Galois-Pill 2 to the power 4, such as x to the power 4 plus x plus 1, x to the power 4 plus x cubed plus 1, and so on. Step 2. S-box is considered with the multiplicative inverse over the Galois-Pill 2 to the power 4 using an irreducible polynomial. The multiplicative inverse m1, m2, and m3 are constructed from irreducible polynomials. 3 S-box has been generated from the multiplicative inverse of 4-degree irreducible polynomials presented in this table. The bold rows are the 3 S-boxes, which we need to modify with affine matrix. An affine transformation can be applied to attain a robust S-box. This transformation rearranges the elements of the S-box. However, the resulting S-box properties remain unchanged. These techniques enhance the complexity of the algebraic expressions of a S-box, which makes the S-box stronger against static and differential attacks. According to Zheng et al., we have accounted for 3 best affine matrices. We have transformed irreducible polynomial x to the power 4 plus x plus 1 using affine matrix 1, an irreducible polynomial x to the power 4 plus x cubed plus 1 using affine matrix 2, and so on. This table shows the 3 new S-boxes using 3 affine matrices by 3 irreducible polynomials. S-box 1, S-box 2, and S-box 3 are shown as bold in this table. Now we will do performance analysis of the produced S-boxes. The nonlinear transformation is an essential criteria in modern Cipher. It should provide a robust cryptographic character against differential crypto properties such as balance, bijection, difference distribution table, DDT, and boomerang connectivity table, BCT. A boomerang function S, bf2 to the power n twice bf2, gf2, is called balanced when the number of ones and zeros are equal in the output set in the corresponding truth table. If all linear combination of columns are balanced, then Boolean function S is called bijective. According to this, Seismic software can calculate the balance for different S-boxes by the following command. The analysis shows the S-box 1, S-box 2 and S-box 3 all are balanced and bijective. Difference distribution table DDT and BCT. Differential analysis is one of the essential cryptographic methods for evaluating the security of block ciphers. The defense against differential cryptanalysis is highly dependent on the nonlinearity structure of the predefined S-box. In this table, we can see the boomerang connectivity uniformity is 16, and we can also observe the differential uniformity of DDT is 4. The DDT has 16 rows and 16 columns with 265 cells. Each row and column present each output difference from 0 to F for each input difference. 0 represents the absence of that output difference for the following input difference. Too high or too low 0 reveals more information concerning output difference. S-box 1 difference distribution table shows that it has 3 values only, 0, 2 and 4. Each row and column has only one 4. The sum of each rows and column is 16. Therefore, S-box can show good resistance against differential cryptanalysis. Conclusion. In this paper, we proposed a lightweight S-box design that use algebraic methods to fulfill all the requirements of lightweight cryptographic cipher. These algebraic techniques utilize 3 irreducible polynomials from the Galois field 2 to the power 4 and creates 3 hexadecimal table. 3 multiplicative tables raised from 3 hexadecimal tables of irreducible polynomials. Then using Affine transformation, 3 S-box are constructed, which are S-box 1, S-box 2 and S-box 3. The cryptographic analysis demonstrates strong resistance to different cryptanalysis. In future, produced S-box should be subject to further testing and utilized for lightweight block ciphers to protect network interaction between IoT resource-constant devices. This approach creates S-box that are suitable for resource-constant devices. S-box can also be used to provide a lightweight block cipher for IoT network communication. This is the reference. Now is a question answer session. Thank you very much for your time. Thank you.